Welcome back to our ongoing series on the OEIS for number theory students. Today we're doing a deep dive into, well, a pretty fascinating sequence, A000229.
Ah, yes. This one connects primes and quadratic residues in a really specific way.
Exactly. So maybe let's start with the basics. Quadratic residues and non-residues. What are we talking about there?
Sure. So take an integer nar. We say a number $2 is a quadratic residue modulo. If you can find some integer $6 such that 6 squared gives you $2 when you reduce modulo mod.
Right. $6 give equally equiv q mod, and modulo 5,4 is a residue because 2 into 2 to tellers is 4.
Precisely. And if you can't find such an $6, then teller is a quadratic non-residue modulo not.
Okay. And there's this nice property for odd primes, right? Like
Yeah.
$2.
Yes, exactly. If you look at the numbers from 1 up to $p, exactly half of them are quadratic residues and the other half are non-residues. So P1, $2 of each.
That's a neat balance. And that leads to the Legendre symbol.
It does. The Legendre symbol written in teller is just shorthand. It's 1 if there is a residue modulo 1, minus 1 if it's a non-residue.
And 0 if teller actually divides a dollar.
Right. It's super useful.
Okay, so with that background, let's get to the main event. OEIS sequence A000229. What defines this sequence at M?
So M is defined as the least positive integer dollar such that the long prime number, let's call it $2.
Like P222, P23, P355, and so on.
Exactly those primes. We want the smallest dollar where TIS is the least quadratic non-residue modulo dollar.
Whoa, okay, so two conditions there. PIS has to be a non-residue modulo dollar?
Yes. And crucially, every positive integer smaller than PS, so $1, 2 dots, PN11, must all be quadratic residues modulo dollars.
Ah, I see. So PPR is the first number you hit that doesn't have a square root modulo.
That's the key. It's a very specific structural requirement on null dictated by the knots prime.
It really ties the prime sequence to this modular property.
It does, and it's why it's interesting. You're seeing how the sequence of primes influences this multiplicative structure.
Okay, maybe we can make quadratic non-residue a bit more concrete. How do we find them? You mentioned checking sex by dollar equiv q mode or not.
Right. And you don't have to check all possible $6 because empty 2 and N-will are the same modulo. You really only need to check $6 from dollars up to, floor of $10.
Makes sense. Save some computation.
Math World has some tables that are helpful here. They list non-residues for small dollars, like for ON3 to 3, the only non-residue among 1, 2 is 2. For N5 and 2 and 3 are non-residues.
So the smallest non-residue for Illinois and $3 and for N of is also 2.
Correct. And the sequence of these smallest quadratic non-residues for N3, 4, $5 is actually another OEIS sequence, A020649.
Okay. And what if we only look at prime moduli, PPDOS? Is there a sequence for the smallest non-residue then?
Yes, that's A053760. It starts 2, 2, 2, 3, 2, 3, 2, 5. You can see it's often 2, but not always. For $200, the smallest non-residue is 3. For Fear Power to 203, it's 5.
So it jumps around. Is there any limit to how large that smallest non-residue can get relative to $2?
That's a big question in number theory. Unconditionally, we don't have a great bound. But if you assume the extended Riemann hypothesis, the ER8.
Which is a major unsolved hypothesis.
Indeed. But if it's true, then we know the first non-residue modulo is pretty small. It's less than log P2.
Okay, log P2 is much, much smaller than PD itself. That's quite a strong prediction.
It is. It tells us we expect to find a non-residue relatively quickly.
All right, let's bring it back to A000029. We have AN as the smallest dollar, where $2 is the least non-residue.
Correct. So for N11 on a view, we want the smallest dollar where 2 is the least non-residue. That means 1 must be a residue. Well, 1 is always $2, so 1 is always a residue.
So we just need 2 to be a non-residue. What's the smallest dollar where 2 is a non-residue?
We saw that for Angum $3, $2 is a non-residue. Are there smaller dollar for $100 and a lon of $22? The concept isn't quite the same. So 1 all lon equals 3, 3.
Okay. What about 1 on 2, 2? That's 2, $3. We want the smallest dollar where 3 is the least non-residue.
Right. So 1 must be a residue and 2 must also be a residue modulo dollars and 3 must be a non-residue.
Let's try small null. 1 unit equiv 1 is his rest, 2 is non-rest. Doesn't work. 3 isn't the least non-rest. 1 wing or where to go in. 22 equiv 0. 32 equiv 9 equiv 1. Only 1 is a residue among 1 with only 3. No, 1 unit is rest, 2 is non-rest. Doesn't work. 1 equiv all 1, 52 equiv, others non-rest. 22 equiv all 3, 32 9 equiv 3, 3, 42 equiv 52 dollars off. You need to be careful with composite moduli. Mod 1 equals rest, $12 1, 22 equals 32 equals 32 9 equals 32, 32 there's 356. Smallest non-res is 3. Does that work? Let's check. Modulus 7, 1 is a residue, 12 the 2 toads, 2 is a residue, 3 2 down is for 3 is a non-residue. So yes, 3 is the least non-residue. Modulus 7 is 7 the smallest. We check 1, 3, 4, 5, 6 here. Seems plausible. So toe under to quickle. Okay, so the sequence starts any 2 on Carones. It feels like finding these dollars could get complicated quickly.
It can. You're essentially solving a system of quadratic congruences and non-congruences.
I saw MathWorld also has tables related to this, like values of done such that the smallest quadratic non-residue. How does that connect?
Right. Those sequences, like A025020 for 220 for 2 occurs, list the moduli in dollars for which 2 is the smallest non-residue. A025021 does it for 232 and so on.
So they fix the non-residue first and find the moduli.
Exactly. And 000229 flips it. We fix the prime p-dollars that we want to be the least non-residue, and then we find the smallest modulus dollar that makes it so.
It's a subtle but different question.
Definitely.
Now, you mentioned this seems kind of irregular, but are there tools to get a handle on this? You brought up the Legendre symbol.
Yes. And the big tool, especially for prime moduli, is the law of quadratic reciprocity. It's, well, quite remarkable.
Remind us what it says.
For 2 different odd primes, primey tip is month, it connects the Legendre symbol PQ to P. Specifically, PQ2 times K12 equals dollars raised to the power frac P12 times frac Q12.
So knowing if a power is a square mod calar tells you something about whether talers is a square mod P.
Essentially, yes. It provides this unexpected link between seemingly independent modular systems. It's incredibly powerful for calculations and proofs.
Okay. And going back to the size of the least non-residue modulo, a prime pet, let's call it MPO, what do we know about its size?
Well, first, an interesting fact. 9p is always prime itself, except for B22, where it's not well-defined, and 2, 3,
But
where
it's prime. That's cool.
it is. And heuristically, you might think the chance of 1 being a residue is 1. The chance of 2 being a residue, given 1 might be roughly 12. The chance of 3 being a residue, given 1 and 2, are maybe 12 again.
So the probability that the first caliber primes are all residues might be like 12 color.
Sort of. That's the heuristic idea. It suggests that NumP might not grow too fast, maybe something like log 2 power.
But what are the rigorous bounds?
The best unconditional upper bound we have is from Burgess, which is roughly NumP is less than power, 1, it's less than 1 Feb2, roughly. Still potentially large, but significantly smaller than Taylor.
And conditional on the Riemann hypothesis.
That's where we get the much stronger bound. NumP is less than a constant times due to Ankeny.
Log squared is tiny compared to PL.
Very much so. And there are lower bounds, too. Graham and Ringrose showed that nunc must be at least like log P, log L, log PP for infinitely many primes.
It can't be too small all the time.
Right. And under GRH, Montgomery showed it's at least log log PT. So there's this interesting range where it's believed to live.
Okay, this is fascinating stuff. For the number theory students listening, why is getting familiar with quadratic residues, non-residues, and a sequence like A000229 valuable?
Oh, it's fundamental. Quadratic residues pop up everywhere. Primality testing, some algorithms rely heavily on them. Cryptography, things like the quadratic residuosity problem, underpin certain crypto systems.
Okay, some practical applications too.
Yes, and theoretically, they're deeply connected to quadratic forms, class field theory, really central concepts. And A000229 specifically is great because it forces you to connect the sequence of primes, kind of an additive structure, with this multiplicative structure of squares modulo dollars.
It makes you think about how these different aspects of numbers interact.
Precisely. Exploring sequences like this, seeing these connections, is really how you deepen your understanding and appreciation for the intricate beauty of number theory.
It really shows the power of the OEIS as a tool for exploration, too.
Absolutely. It's a fantastic resource for seeing patterns and finding these kinds of links.
So to wrap up, we've looked at quadratic residues and non-residues, the Legendre symbol, and this specific sequence, A000229, where AINs is the smallest modulus smaller, making the NOR5 prime piconuller the very first non-residue.
That's the essence of it. It's a sequence defined by this specific interplay between primes and modular squares.
A really interesting challenge problem baked into a sequence definition.
Yes. And maybe a final thought for you to ponder. We know the distribution of primes has irregularities, gaps, twin primes, all sorts of behaviors. How might those irregularities influence the values in the sequence?
Like, could a large gap between primes affect the search for the modulus dollar?
Or could properties of 2p dollars itself, like whether it's a twin prime, influence the corresponding at? It makes you wonder about those deeper connections, what patterns or perhaps surprising jumps might appear in A000229 down the line.
That's a great question to think about. We definitely encourage you to explore quadratic residues, maybe play with the law of quadratic reciprocity, and certainly look up A000229 on the OEIS. Thanks for joining us for this deep dive.